By 2020, the transformer had conquered natural language processing, but computer vision was still ruled by convolutional networks, which had dominated for nearly a decade. Then a team at Google Brain asked a wonderfully simple, almost reckless question. What if we stopped treating images as grids of pixels, and instead treated an image as a sequence of words and just fed it to a standard transformer? No convolutions at all. The paper is called An Image is Worth 16 by 16 Words, and this is the model it introduced, the Vision Transformer. To see why this is bold, picture two separate worlds. In language, the transformer reigns. It's pure attention, it has very few assumptions baked in, and it scales beautifully. Pour in more data and compute, and it just keeps getting better. In vision, convolutional networks reign. They come with strong, hand-designed assumptions about how images work. These two worlds had grown up apart. The question this paper dares to ask is whether the clean, scalable language recipe could be applied, almost unchanged, directly to pixels. Here's the whole architecture on one slide, and the beautiful thing is how little is new. On the left, the image is sliced into patches that get turned into tokens. Those tokens flow into the block on the right, which is just a standard transformer encoder, the same machinery used for text. At the top, a single output is read off to make the prediction. The genius isn't a fancy new component. It's the translation step that lets an image pretend to be a sentence. Let's build that step by step. First, the translation. Take a typical 224 by 224 image and cut it into a grid of small patches, each 16 pixels by 16. That gives you 196 patches. Now flatten each patch, 16 by 16 pixels across 3 color channels is just a list of 768 numbers. Pass that through a single linear layer, and each patch becomes one neat token vector. An image is now, quite literally, a sentence of 196 tokens. But there's a subtlety. Self-attention is order blind. Shuffle the tokens and it can't tell. For text that's a problem, and for image patches it's a disaster, because where a patch sits clearly matters. So we add a learned position embedding to every patch, a little vector that says where I came from. Then one more trick borrowed from language models. We prepend a single extra learnable token, the class token. After the network runs, its final state serves as the summary of the whole image, and that's what we classify. Now the easy part, because there's almost nothing left to invent. The sequence of patch tokens, plus their positions and the class token, is fed into a completely standard transformer encoder, the very same design from natural language processing. Inside, multi-head self-attention lets every patch directly look at every other patch, anywhere in the image, right from the first layer. Notice what's missing. There are no convolutions, no pooling, almost nothing about images is hard-coded. The model has to learn how vision works from scratch. And that freedom comes at a price, which is the paper's most important result. Look at this plot. When the vision transformer is trained only on ImageNet, a medium-sized dataset, it actually loses to the convolutional baseline, the gray line. Pre-train it on the bigger ImageNet 20K and it catches up. But pre-train on JFT, 300 million images, and the transformers, the colored dots, pull clearly ahead. The lesson: this model is hungry. Give it enough data, and it overtakes the networks that ruled vision for years. So why does it need a mountain of data when a convolutional network gets by on far less? It comes down to inductive bias, the assumptions baked into a model before it sees any data. A convolutional network has two powerful ones built in: locality, the idea that nearby pixels belong together, and translation equivariance, that an object is the same wherever it appears. The vision transformer is handed almost none of this. It must learn those facts about images itself, and learning them from scratch simply takes a lot more examples. Here's the flip side, and it's the reason people got excited. If you measure performance against the amount of compute spent pre-training, the vision transformers, the blue dots, sit above the ResNets, the gray squares, almost everywhere. For a fixed compute budget, the transformer tends to reach higher accuracy. So it isn't just that they can match convolutional networks. Given the same resources, they often make better use of them. That combination, scalable and efficient, is exactly what made the language transformer so dominant. And the payoff was real. The largest model, VTAB, pre-trained on JFT, and then transferred, matched or beat the best convolutional systems of the day across a wide sweep of benchmarks. The 19-task VTAB suite, natural images, specialized medical and satellite imagery, and structured tasks. It did this while taking substantially less compute to pre-train than the top convolutional competitor. A pure transformer fed pixels as patches had reached the frontier of computer vision. It works, but does it learn anything sensible inside, or just memorize? The authors looked, and what they found is reassuring. This shows the linear patch embedding layer, the very first step, visualized. Even though we never told it to, it has learned filters that look like edge detectors, color blobs, and little textures strikingly similar to the first layer of a convolutional network. Given freedom and data, it rediscovered some of the same basic visual building blocks by itself. Remember those position embeddings, which started as random vectors with no idea of geometry? This grid shows how similar each patch's learned position vector is to every other. The bright diagonal structure means patches in the same row or the same column ended up with similar embeddings. In other words, with no hints at all, the model figured out the two-dimensional layout of the image, that this patch is near that one, purely from the data. Now, the biggest difference from a convolutional network. A convolution can only see a tiny local window in its early layers. Its view widens slowly with depth. This plot measures how far, on average, each attention head looks. Notice that even in the very first layers, some heads already reach right across the whole image, the high dots, while others stay local. The Vision Transformer has the option to be global from layer 1, and it learns to use both near and far information at once. And when you trace what the model actually attends to, from its output back to the input pixels, you get this. It consistently focuses on the parts of the image that matter for the label. The dog, not the grass. The airplane, not the sky. The snake, not the leaves. Despite having no built-in notion of objects, the Vision Transformer learns to attend to semantically meaningful regions, much like we would point to the thing in the picture. Step back, and the significance is hard to overstate. This paper showed that convolutions, long thought essential to computer vision, are not actually required. With enough scale, a plain transformer and raw attention can match or beat them. It meant a single architecture could now span both language and vision, a major step toward unified models. And it opened the floodgates. The Vision Transformer became a foundation for much of modern computer vision that followed. Sometimes the boldest idea is to take what already works and simply refuse to complicate it.